Hello everyone, today we're going to be going over the January 2025 Chemistry Regents exam. In this video we're going to be focusing on Part C, which are the last 20 short response questions. A link to this test can be found in the description of this video if you want to follow along at home. That being said, we're going to go ahead and start off with number 66, which asks us to identify the two types of bonding in the compound used to make plaster casts. So over here we have the medical use and here we have the formula. So the compound that's used to make plaster casts is CaSO4. So CaSO4. What types of bonds are happening in the CaSO4 molecule? Well, we know that in chemistry we have metallic, we have ionic, and we have covalent bonds. Metallic bonds are between two metals. Ionic bonds are between a metal and a nonmetal, and covalent bonds are between two nonmetals. Right, so which one of these bonds can exist in the CaSO4? Well, obviously it can't be metallic bonding because for you to have a metallic bond, you need to have a metal bound to another metal. How many metals do I have here? Well, if I look at my periodic table of elements, I know that calcium is my only metal here. Calcium is a metal. Sulfur and oxygen are both non-metals, okay? So obviously can't be metallic bonds. So I'm left with ionic and covalent bonds as my right answer. All right, if you want to think about it a different way, you can always split up an ionic molecule, right? Something that has metal and non-metal into a metal and a non-metal side, obviously. In this case, calcium is my metal, so this is going to be on my metal side. And this SO4 is going to be on my non-metal side. Okay, but you might be asking, well, there's two nonmetals here. Why is that? Well, that's because we're dealing with a polyatomic ion, okay? What does polyatomic ion mean? Well, poly means many and atomic means atoms. So a polyatomic ion is just two atoms combined that has a charge, right? An ion is something with a charge. So in this case, an SO4 is what we call a sulfate because it's a sulfur combined with four oxygens, right? That's multiple atoms that has a charge on it. Right? So it's not the sulfur binding to the calcium, right? It's not the oxygen binding to the calcium. It's this molecule of SO4 that's binding to this calcium. But the key word here, the takeaway here is that this SO4 is regardless, it's treated like a nonmetal. Okay, why? Because it's made up of nonmetals. So this SO4 is its own unit or its own molecule that's then being attracted to this calcium, okay? So what's happening? Well, this attraction between a metal and a nonmetal is an ionic bond. And then if we look at this unit, well, what's happening between this sulfur and this oxygen? Well, a covalent bond is forming between these two nonmetals, okay? So the correct answer for 66 has to be an ionic and a covalent bond. Those are the two types of bonding. All right, moving on to 67, it asks us to identify the noble gas that has atoms in the ground state with the same electron configuration as the positive ion in MgOH2 in the ground state. All right, so notice here how MgOH2 is made in the same way that CaSO4 is. It's a metal over here that's bound to a polyatomic ion, right? It's an ion. This OH has a charge, and it's made up of many atoms, right? In this case, more than one atom means poly, so this O and this H. So what do you mean it has a charge? Where is its charge? Well, let's look at the table right here. We know that OH is what we call a hydroxide, and it has a charge of -1. Okay, so this MgOH2 is a bond between this magnesium and these two OHs that each have a charge of -1. Well, you might be asking, well, why is there no charge on the overall molecule? And that's because this magnesium had to cancel out that -1 charge from the OH. Oh, so you might be saying that the magnesium has a +1 charge. That's wrong. Take a look at this number right here. This MgOH2 means that there's two hydroxides in this molecule of MgOH. What that means is, well, what I just said. There's two OHs here, which means that if each OH has a -1 charge, overall, these OHs are contributing a -2 charge to this magnesium. So this actually has a -2 charge over here because of these two -1 OHs. But if overall this molecule has no overall charge, that means that this magnesium has to have a +2 charge because +2 minus 2 is equal to 0, right? So combining these two charges yields an overall charge of 0, which means it's neutral, which is what it is, all right? So if I have an Mg2+, what's its electron configuration? Well, you know that whenever you have an ion, you're dealing with changing the number of electrons. If an electron is something that's negatively charged, if you want to make something more positive, are you going to add more negative charges or are you going to get rid of the negative charges? So again, to make something more positive, are you going to get rid of whatever's making it negative, or are you going to make it more negative by adding more negative charges? You're going to get rid of whatever's making it negative, okay? Each one of these electrons carries a -1 charge. So if I have a magnesium and I get rid of one of its electrons, I get an Mg+1. And if I get rid of another one of its electrons, I get an Mg+2, you guessed it, right? Each negative charge I remove, I get an opposite charge. So I get a plus charge in that case. So this Mg2+ was formed by taking away two electrons, okay? So let's look at the electron configuration of magnesium or Mg. So if we look at the electron configuration here, it's going to be this string of numbers at the bottom of the atom. So this example here, this tells you the electron configuration of carbon is 2-4. For magnesium, it's 2-8-2. And you know that electrons are removed from the outermost position all the way to the innermost position. All right, so this is the innermost shell, this is the middle shell, and this is the outer shell. So if you're removing electrons, you're going to take them from the outer shell first. So to make Mg2+, we took away 2 electrons, which means that we took away 2 electrons from the outer shell. Now there's nothing in that shell, so the new electron configuration is 2-8. Right? So which other molecule here, or which other atom here, has a configuration of 2-8? And obviously that's going to be neon right here. And that's also a noble gas because it's in the noble gas group, which is the last group, the rightmost group, or the rightmost column. So the correct answer here has to be neon or Ne. All right? Moving on to number 68. It wants us to find the electron negativity difference for the bond between zinc and oxygen in zinc oxide. So whenever you want to find the electron negativity difference, you find the electron negativity of the non-metal, and you subtract that from the electron negativity of the metal. All right? How do you find that? Go to table S. Here you have a column that literally says electron negativity. I already highlighted it. Oxygen has an electron negativity of 3.4. Remember that oxygen is a non-metal, so we'd do 3.4 minus the metal, which is zinc here, and zinc has an electron negativity of 1.7. So 3.4 minus 1.7 is equal to 1.7, which is going to be the correct answer here. So we just write in 1.7. Right, number 69 asks us to compare the freezing point of water at standard pressure to the freezing point of KNO3, or potassium nitrate, at standard pressure. So which one of these is going to have a higher or lower freezing point? Well, obviously it's going to be KNO3. Whenever you have a solution with something dissolved inside of it, meaning that it is a solution, it's always going to have a lower freezing point, okay? So we just say here how did not mean to do that, guys, oh my goodness. It says that KNO3 has a lower freezing point. This is just something that's always true. You just need to remember this. Any solution that has something dissolved in it always is going to have a lower freezing point. We'll put that as an aqueous solution. Why? Because this KNO3 kind of disrupts the bonds that need to form in order for you to make an ice. All right. So if you had just water here, just H2O, in order for it to turn into a solid, you need to reduce the energy of these H2O molecules so that they're able to not move as much and form these bonds, right? So now the structure becomes very stable because it has all these bonds here. All of a sudden, if you have potassium nitrate that you dissolve into solution, you're now adding molecules of potassium, or atoms of potassium and molecules of NO3, or nitrate. They're much bigger than the molecules of H2O, and they're actually going to disrupt this bonding over here, right? They're going to take up that space, and as a result, this water, the molecules inside of the water, have to bond around these disruptions, which means that they have to get rid of more and more energy in order to overcome, the difference here, right? Or the change in the shape to reform that grid, which means that KNO3 in an aqueous solution, meaning that it is in water, must have a lower freezing point, right? You have to take away even more energy for it to account for the disrupted grid. Number 70 asks, based on table G, classify in terms of saturation the type of KNO3 solution made by the student, okay? So if we go ahead and scroll up to table G, here's what we'll find. We have a bunch of curves, right? So we need to first identify the KNO3 curve because we're talking about KNO3. Here's that curve. I'll just highlight it in red. So essentially, this plots temperature. We know that we're dealing with 25 degrees Celsius, which is right here. And it's dealing with grams of solute. All right, so if you have a solution, it's going to obviously be filled with a liquid. The liquid here is going to be what we call the solvent. And then you're going to add something to this solvent to create a solution. So in this case, the KNO3 was a solid. You added it to the solution, and it dissolved to produce KNO3, which is now an aqueous solution, meaning that it's in water. So whatever you're adding to the mixture, whatever you're adding to the liquid is the solute, and whatever the liquid is the solvent. Okay, so in this case, it's grams of solute per grams of solvent. Water is always a solvent, okay? And aqueous means it's in water. So that gives it away that water is a solvent. So KNO3 aqueous, the KNO3 has to be the solute. So we need to find the grams of solute that we add here. We understand that we have 0.1 mole of potassium nitrate, KNO3. And we know that every 1 mole of potassium nitrate weighs 101 grams, okay? So set up a dimensional analysis. If you're confused, do I divide 0.1 by 101 or do I multiply 0.1 by 101? Set up the units, right? If you want to get rid of moles, to get grams, you need to have moles in the numerator and moles in the denominator. The conversion here is 101 grams per mole. So do I have to flip this or do I keep it the same? Well, if I keep this conversion factor the same and I multiply it by 0.1 mole, I have moles in the numerator, moles in the denominator. That means that those two cancel out. And I'm left with 0.1 times 101 grams, which is just 10.1 grams. Guess what? I wanted grams, so this is the correct way. If I wanted to do this the other way, 0.1 moles times 1 mole over 101 grams, if I didn't flip this conversion factor, or if I just divided 0.1 by 101, the moles would not cancel out, and you'll be left with moles squared over grams, which is not what we want here. We just want grams of solute. So either way, we have 10 grams of solute, okay? Now, if I were to plot this point, we see here how 10 grams of solute, or 10.1 grams of solute at 25 degrees Celsius, leaves us right here. This is my point. Now, you might be saying, well, what type of solution is this? Well, whenever the point is underneath the graph, you have something that's unsaturated, meaning that you can add more solute to be dissolved. If you have something that's on the actual line, that means that you're saturated. This is the most amount that you can dissolve before a solid forms on the bottom, right? So that's the maximum amount that you can dissolve in the solution. And finally, if you have a point that's above this line, right, above your solubility curve for this specific substance, that means that you're super saturated. So you've added too much, and now the salt or the whatever solid you're adding is no longer dissolving because the solvent dissolved as much as it can, right? That means it's super saturated. It's too filled with solute. So as a result, it cannot dissolve anymore, right? So in this case, we know that our original point that we plotted was below the line, which means that it has to be an unsaturated solution. So unsaturated. That's all we had to put, and now we can move on. All right. Number 70 or 71 says, describe a laboratory procedure that the student can use to separate the original KNO3 from the KNO3 aqueous solution. So whenever you want to get your your solute back, whatever you dissolved back from the solution, you can always just evaporate the solvent or or you can just boil it out. So you can say that you can boil the solvent, which in this case was H2O, or you can evaporate the solvent, and that's all you have to do here, right? Remember that whenever you have a solution, you have your salts, or whatever your solid was, dissolved in this mixture, right? If you all of a sudden boil this, well, you're turning this water, this H2O liquid, into an H2O gas, which means that it can now escape out of the container. As it's escaping, it's not bringing these KNO3s with it because it doesn't form a bond with them. All right, so the KNO3 or the potassium nitrate is left over in this container, and you've essentially just boiled out the water, and now you only have the solid left. Right, number 72 through 74. 72 asks us, state in terms of reactants and products why the chemical reaction represented by equation 1 is a synthesis reaction. So what does synthesis mean? Just in general, to synthesize something means to create something. All right, so this is a synthesis reaction because you're creating one thing. All right, two things are coming together to create one thing. All right, you have synthesis reactions and you have decomposition reactions. So to decompose is to break something apart. So decomposition reaction would look like AB turning into A plus B. So we split this into two products. A synthesis reaction is A plus B turning into one molecule of AB. So you can say here that a reason why this is a synthesis reaction is just that, right? You have two molecules / substances are turning into one, or two molecules form one product or one molecule, right? Anything that just says that two things are combining into one will get you full credit here. Number 73 says on the labeled axes in your answer booklet, draw a potential energy diagram for the reaction represented by equation 1. All right, so this is going to be a reaction, and you have to map it based on the energy. Okay, so the energy here is going to be the y-axis, and the reaction coordinate just over time. So you're always going to start off with a flat line. This flat line is going to represent the energy of the reactants. Okay, it doesn't matter where you draw this as long as you don't draw it all the way down here. All right, then what you need to do is you need to draw a curve going upwards, just a bump. All right, it doesn't have to be crazy high, it doesn't have to be crazy low, just a bump. Okay, so in this case we can go bump and make sure that you go down a little bit. All right. Now, here's the difficult part. You need to figure out where you draw your second line. And there's two places you can draw your second line. After you draw this bump represents the activation energy, right? So it doesn't matter how high or how low you draw it. All you need to do is you need for it to actually go up, right? A bump. So this is energy that you need input for the reaction to happen, and then it needs to curve down a little bit, right? Now, you need to draw a second line, either above the line of the products or below the line of the products. And this matters based on what type of reaction occurred. So if we look at reaction 1, we know that energy is released, right? Energy is also a product. So if energy is released, that means that energy was lost by the reactants, right? Where is this energy coming from? Well, it's coming from the reactants, right? If the reactants had a high energy and the product has a low energy, in order for energy to be conserved, right, let's think about it this way, right? Let's say that the NH3 had 2 kilojoules of energy inside of it, right? That's just how much change it could force to happen, right? It had that much energy in it. It was that excited. And when it combined with this HNO3, let's say that it had 1 kilojoule of energy, right? Well, obviously, you would think that 2 kilojoules plus 1 kilojoule equals 3 kilojoules, right? So this NH4NO3 would have 3 kilojoules. But no, actually, it only had 1 kilojoule of energy. But remember that energy has to be conserved. So if on this side I have 3 kilojoules, but on this side I only have 1 kilojoule, I have to add another variable, which is energy, right? In order to balance this 3 kilojoules with this 1 kilojoule, I need to add 2 kilojoules of energy that's being released, right? So if we look at this side, the product has 1 kilojoule of energy, and of course someone has to, rev their engine right outside. Sorry, guys. Anyways, so of course, if we have 1 kilojoule of energy, we have to draw these 2 kilojoules of energy getting released. So our products had our reactants, right, what we started with, had 3 kilojoules of energy in total, and our product had 1 kilojoule of energy in total. So should our bar, that represents the amount of energy that our product had, be higher or be lower than our reactants? Well, it should be lower than our reactants because we started off with more energy. And this decrease, this dip here, represents that plus energy that was released to the system, okay? And this is, again, what we call an exothermic reaction. Number 74 asks us to compare the rate of the forward reaction to the rate of the reverse reaction in the equilibrium system represented by equation number 2. So if we look at equation number 2 here, we know that it has this weird line right here, right? Instead of putting a single arrow, it has an arrow going forward and an arrow going backwards. Whenever you see this, that means that the system is in equilibrium, which means that the rate of the forward reaction is equal to the rate of the backwards reaction, right? That's how you get equilibrium. So all we have to do here is that just say that the rate of the forwards reaction is equal to the rate of the backwards reaction. So again, the reaction is going both ways, right? This NO2, this 2NO2 is turning into N2O4 plus energy, and at the same time, this N2O4 plus the energy that's released is turning back into this gas right here, right? So it's shifting, right? It's going to the right, but at the same time, it's going to the left. And there's a certain rate at which going to the left equals the rate at going to the right. When the forward reaction reaches the backwards reaction, when it undergoes at the same amount or the same rate, you have equilibrium. So think about it as people like entering and leaving a room over time, right? So let's say that 3 people enter the room and 3 people exit the room. We would call this equilibrium. Why? Because the amount of people in the room isn't actually changing, right? Think about it. If I have 5 people in this room, 3 people come into the room, that's 8 people. Then 3 people at the same time, 3 people leave. We're back at 5 people. There's no net change and it's equal, right? It's an equilibrium because there's no net movement in any direction. You're not increasing the people in the room and you're not decreasing by the people in the room because the people entering, the forward reaction, is equal to the people exiting, which is the backwards reaction. Right, so number 75 asks us to state the number of hydrogen atoms in a molecule of hexane. So I know that I haven't really been reading these blurbs here because I don't think you guys need to read them, but this is a case where some students might get tricked up. If we read this, it says that pentane, heptane, hexane, and octane are components of gasoline. The structural formula below represents a single straight change molecule of pentane. So what a lot of students would do here was they would just assume that this is a molecule of hexane. And they would count the hydrogens. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. I hate to break it to you guys, the answer is not 12 because this is a molecule of pentane. We're asking about hexane here. So don't look at this diagram for number 75. Okay, we have to look at something else. What this does tell us is the structure or the general structure that pentane, hexane, heptane, and octane are going to follow. And that structure is a solid backbone, or just a straight backbone full of carbons, all right? And the amount of carbons is determined by its name. For example, pentane has 1, 2, 3, 4, 5 carbons because, well, pent means 5, right? Think pentagon. Pentagon has 5 sides. Hexane, well, think hexagon. Hexagon has 6 sides. Heptagon has 7 sides. Octagon has 8 sides. If you don't want to remember all that, you can scroll down here into the organic chemistry section, and we see how, hex means 6, pent means 5, hep means 7, okay? So if we have heptane, that means we have 7 carbons. If we have hexane, we have 6 carbons. And if it's following this structure, that means that it just has 6 carbons in a straight line with a single bond between them. So this is 1, 2, 3, 4, 5, 6 carbons. And we know that each one of these carbons is going to have a hydrogen bound to it. So if I have 6 carbons, that means that here's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, and 14 hydrogens surrounded by it, right? So the correct answer here has to be 14 hydrogens. All right, number 76 says, state in terms of carbon-carbon bonds why octane is a saturated hydrocarbon. Whenever something is saturated, it only has single bonds between the carbons, okay? So we know that if we look at a molecule of octane, it'll be the exact same as pentane and hexane, just with 3 or 2 extra carbons attached to it, right? So 1, 2, 3, 4, 5, 6, 7, 8. This is what a molecule of octane looks like, right? It just looks something like this. And we understand that this is saturated because it only has carbon single bonds. So the correct reasoning here would be that it only contains single bound carbons. And a better answer would be, or instead of saying single bound carbons, or carbons bound by a single bond. Because think about it this way, right? Each one of these carbons has to share 4 electrons. Each one of these hydrogens has 1 electron to share, right? And each one of these carbons has 1 electron to offer. So if I have a single bond between all of these, that means that all of my carbons are filled with hydrogens, right? Let's look at this molecule of pentane. Each one of these carbons has 1, 2, 3, or 1, 2 hydrogens. If all of a sudden, let's say that I change this bond to a double bond, right? How many electrons would I be sharing now? If each line represents 2 electrons, this would be 2, 4, 6, 8, 10, right? At most, you can share 8 electrons. So what this means, if there is a double bond between this carbon and this carbon, that means that you would have to get rid of one of these hydrogen bonds. Let's get rid of this hydrogen bond over here. You can see here how you have 2, 4, 6, 8 electrons that you're sharing, which means that this is all good. Over here, you have 2, 4, 6, 8, 10 electrons. So again, you have to get rid of a hydrogen here. So to accommodate this double bond, you have to get rid of 2 hydrogens. Now, is this saturated anymore? No, this is not saturated. Saturated means full. Is this full of hydrogens? No, it actually has 2 gaps where hydrogens could have gone, but don't go because of this double bond in the carbon right here. But again, you can't just say, oh, every carbon is filled with hydrogens, because it's asking us to state in terms of carbon-carbon bonds. For you to have 1 hydrogen for every single carbon, what needs to happen is you need to only have single bonds between the carbons, okay? You could have also said there's no multiple covalent bonds between the carbons, which means that there's no double or triple bonds between the carbons, which is why it has to be saturated. Number 77 finally asks us to draw a structural formula for a straight chain molecule of heptane, okay? So straight chain meaning that there's just a straight line of carbons, and we know that heptane means 7. So we'll just draw 7 carbons. 1, 2, 3, 4, 5, 6, 7. And then again, because it's a heptane molecule and it's saturated, each one of these has to have a hydrogen bound to it. So here's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, and 16 hydrogens bound to it, and that's the correct answer, right? The way that you would get this wrong is if you drew anything other than single bonds here, or if you bent the carbons going up like this, right? It's a straight chain, which means that there's no bends. Right, moving on to number 78, it asks, state in terms of energy why the power source is required for the cell to operate. Okay, so this is our cell right here. It says that chlorine gas and sodium metal are two valuable industrial elements that can be processed in an electrochemical cell by an electrolytic reaction. In the reaction, liquid sodium chloride is separated into two elements by an electric current. The simplified diagram and equation represents this process. Okay, so what's happening here is you have a power source, meaning that energy is being inputted, and you have this NaCl, or the sodium chloride, turning into liquid sodium and chlorine gas. It's asking, well, why is power required here? And that's because this is an electrolytic reaction. Literally, electrolytic means that you need an input of electricity. So you can say here how all electrolytic cells or reactions need electrical energy. Remember, you have electrolytic cells and you have galvanic cells. Galvanic cells are spontaneous, meaning that they can happen on their own, right? They don't need an input of energy. Electrolytic cells always need extra energy because it's non-spontaneous. You could have also said that this reaction is non-spontaneous, so it needs energy from an outside source, or you could say that the power source causes the non-spontaneous reaction to occur. Whenever you need an input of energy for a reaction to start, we call that non-spontaneous, right? Because you need some sort of motivation to happen, right? Think about a spontaneous hangout between you and your friend, right? It just happens out of thin air. No motivation nor excitement is required because, that comes from within. If someone is asking you to hang out or you're forced to hang out with someone, then that's non-spontaneous. You made a plan. But if it happens out of the thin air, someone texts you, let's go out, well, that's a spontaneous, and you agree, well, that's a spontaneous plan, right? Happened out of nowhere. No extra motivation was required. No extra planning was required. You're just up and ready to go, right? Non-spontaneous planning was required. You have to be motivated. Oh, well, he'll come, she'll come. Well, I'll pay for your food. Something has to occur. Something has to be inputted into the plans for you to agree to go, right? For you to just randomly get up and go, well, that's spontaneous. Finally, number 79 asks, state the number of moles of electrons lost when 4.0 moles of electrons are gained in this reaction. Okay, so let's look at what this reaction is. This reaction is 2 NaCl turning into 2 Na plus Cl2 gas, okay? So what's happening here is this is what we call a reduction and oxidation reaction, or a redox reaction. How do I know that? Well, number one, the question is asking us about electrons lost and electrons gained. And also, it's an electrolytic cell. When you have an electrolytic cell or a galvanic cell, know the difference between the two of them, they're both harboring redox reactions within them, just in different orders, right? One of the redox reactions needs power to occur, the other does not, right? Galvanic cells don't need power to occur, but there's still a reduction oxidation reaction happening in both of them. To understand this, remember oil rig. Oxidation is losing, reduction is gaining, okay? For a redox reaction to happen, one of these atoms has to lose an electron and the other one has to gain an electron. So how do I figure that out? Well, first of all, whenever something is in its elemental form, right? Whenever something is just an element or alone, we know that it has an oxidation state of 0. So it has 0 electrons right now, right? Or essentially the oxidation number doesn't really tell us the number of electrons there. It's kind of like a number that we use to keep track of the electrons lost or gained, okay? So we know that when you just have sodium, even though it's liquid, when you just have sodium, just Na, it's pure, right? Why? Because it's in a liquid form. If it's in aqueous form, it's with H2O. But either way, we have liquid sodium, right? It's pure. Anything that's a pure element has an oxidation state of 0. Okay, so that's the placeholder we put up there. And the same thing goes with chlorine. Chlorine is a Cl2, it's diatomic, and it's a gas, right? This is also in its natural state. So we put this as 0. It's elemental. It's not combined with anything else other than itself, which means that its oxidation state is 0. Now, if we look at this NaCl, right, the sodium chloride, is the sodium alone? No, it's bound to a chloride. Is the chloride alone? No, it's bound to a sodium. So because neither one of these are alone, we're going to have to assign oxidation states. If we look at our reference table over here, in the periodic table of elements, which to scroll down for, we see here how selected oxidation states are up here. They tell you the oxidation states that could occur in that molecule. And we see here how sodium only has one oxidation state, and that's +1. So when sodium is combined in a molecule, it always has a +1 oxidation state. Now, is NaCl charged? No, NaCl has no overall charge, 0. So if you have a +1 oxidation state on the Na, what oxidation state do you have to have on the chlorine to cancel out the overall oxidation state on this molecule? Well, it has to be -1. Why? Because +1 minus 1 is 0, and NaCl has no number above it, so they have to cancel out. So this sodium has a charge of +1, and then it's turning into a sodium with a charge of 0. So if you're going from +1 to 0, what did I have to add here? Well, I added an electron. I added a -1 charge. +1 -1 is 0. So this sodium gained an electron, okay? Remember, reduction is gaining. So this got reduced. If we look at this chlorine went from -1 to 0. So this lost an electron, right? Meaning that it got oxidized. How do you become more positive? Well, if you're -1, you're negative, and if you're 0, you're neutral. So how does that happen? Well, you go ahead and you lose an electron, right? So this got oxidated. So for every single mole that's reacting here, right? For every single time that this reaction occurs, for every single 2 moles of sodium that are reacted to form 2 moles of sodium, 2 moles of sodium chloride that are reacted to form 2 moles of sodium and chlorine gas, what's happening here is that 1 electron is released and one electron is gained. So if 4 electrons are gained, how many electrons have to be released? Well, for you to gain 4 electrons, you have to have got them from somewhere. In this case, you're getting those 4 electrons from this chlorine that's losing them. So if this sodium got 4 electrons, that means that this chlorine had to have lost 4 electrons. So number 79 has to be choice 4. Or not choice 4, but just the number 4, right? If you're gaining 4 moles of electrons, that has to equal to the number of moles of electrons that you lost. And finally, number 80 asks us to determine the oxidation state that occurs in chlorine in the cell. So if we look at chlorine, its oxidation state was originally -1, and then it turns to 0, so you just write from -1 to 0. All right, last cluster of questions, guys. Finally, it says that the radioisotope uranium-238 changes to lead-206 in a series of nuclear decays that can be used to determine the age of some rock layers. In one step of this nuclear decay series, U-234 produces thorium-230 by alpha emission. The graph below represents the decay of 40 milligram sample of thorium-230. Using the graph, determine the half-life of thorium-230. So the half-life, it just tells you the amount of time that needs to pass for you to reduce half your mass. All right. So for example, if I have a 40-gram sample of uranium-235 and it takes 1,000 years for this sample to decay into 20 grams of uranium-235, my half-life is 1,000 years. That's the time it took for the mass of the sample to halve or to go in half. All right. So let's look at this graph. It tells you the mass versus the time. So here I start off at 40 milligrams. All right. Well, what's half of 40? Half of 40 is 20. So if I look at the half-life, it should be the amount of time that passes between 40 and 20 grams, right? Because that's how you lose, that's the amount of time it took to lose half of your mass. So we know that at 40 grams, well, that's at 0 years. And then at 20, we have to go down here and we see that's just shy of 1.0 times 10 to the power of 5 years. So here, to figure this out, I need to understand what each tick mark means, right? So I'm going from 1 times 10 to the power of 5 years all the way up to 2 times 10 to the power of 5 years, right? And if you're confused as to what that is, that's just do the math. 1 times 10 to the power of 5, well, that's, 100,000. So you're going from 100,000 years to 200,000 years. So how many years are you increasing by, right? If I have 1, 2, 3, 4, I have 4 slots to increase from 1 to 2, well, I have to be increasing by 0.25 times 10 to the power of 5 years, which is just 25,000, right? 25,000 times 4 is 100,000. 100,000 plus 100,000 is 20,000, okay? So anyways, figure out the tick mark, right? Figure out the scales. I know that each one of these tick marks, right, or each one of these hashes represents 25,000 years, or 0.25 to times 10 to the power of 5, okay? So what's 1.0 times 10 to the power of 5 minus 0.25 times 10 to the power of 5? Well, that's just 0.75 times 10 to the power of 5, which is going to be the correct answer here, right? That's the amount of time that it takes for this sample to decay, right? So we can just do 0.75 times 10 to the power of 5 years, or you can go ahead and you can just state 75,000 years, all right? Moving on to number 82, it says that determine the fraction of thorium-230 sample that remains unchanged after 2 half-lives, okay? So let's think about it this way. If you start your decay, right, at your starting point, you have 100% of your mass. Nothing has changed. Then the half-life, well, you reduce your mass by half. So half of 100% is 50%. This is 1 half-life. So now you have 50% of your mass remaining, because in 1 half-life, 50% or half of your mass gets reduced. Then we have 2 half-lives, right? So if this is 1 half-life, what happens during the second half-life? Well, 50% of whatever remaining is going to get reduced again. So if 50% of my sample was remaining, half of what was remaining gets reduced again. So what's half of 50? 25. So only 25% of my sample reduces, right? So the correct answer has to be 25%, or 0.25, or 1 over 4. The trick for this question is to multiply 1/2 by however many lifetimes is happening. So you know that 1 half-life is, well, 1/2. And 2 half-lives is just going to be 1/2 multiplied by 2 because that's the number of half-lives. So if they ask you about, well, what sample would be remaining after 3 half-lives, well, you just multiply this by 1/2 again, right? So that's the trick here. Or you could have just done this. So this is now 2 half-lives because we added 1 from this 1 half-life here. Right, number 83 says compare the penetrating power of a beta particle to the penetrating power of an alpha particle from a thorium-230 atom, right? So here we have a table of emissions here, alpha particle to positrons. The heavier your particle is, the less penetrating it will be, right? The easier it will be to stop it. So if we look at a beta particle, right, the beta particle is represented here. Remember that whenever you, in this notation where you have a number up here and a number down here, right, this 4 is going to be the mass. So in this case, this helium 4,2, this is what we call an alpha particle. It has a mass of 4. This beta particle can be written as E, -1, 0, or as B, which is where we get beta from, 0, -1. We can see here how both ways of writing this list its mass as 0, right? And because you have 0 mass, you're able to penetrate more effectively because you're able to go further, right, with that lack of mass. Less things can stop you. Think about a very small particle, moving through a net, right? The bigger you are, the worse that you fit through that net. The smaller you are, the better you can fit through that net and the more you can penetrate, okay? So obviously the beta particle is better at that, okay? So we can just say that the penetrating power of a beta particle is greater. And we can just move on with our lives. So number 84 asks us to complete the nuclear equation in your answer booklet for the decay of U-238 by writing a notation for the missing product. So what has to happen here is the top numbers have to match up and the bottom numbers have to match up. What that means is right here we went from 92 and here we have 2. So this isn't balanced. What I need to do here is I need to add whatever molecule has, or whatever atom has 90 in that slot, okay? And the number on top also has to match, right? So this 238, you have 238 on the top on this side. That means that whatever molecule is written on this side also has to have 238 when it's added by 4, all right? So the top and the bottom have to match up. So what plus 2 is equal to 92 to keep this the same? Well, 90, right? And remember that this bottom number tells you the atomic number. Okay, so if you have an atomic number of 90, what are you? Well, if you have an atomic number of 90, that means that you have to be thorium, right? Thorium. So we'll write TH, and we'll put 90 here. You know that 2 plus 90 is 92, so this bottom is completed, but what about the top? Well, 4 minus 238 is equal to what? Well, that's equal to 234. So thorium-234 is the correct answer here. Why? Well, because if we add up the top, on this side, well, there's nothing else other than this U238. So that means that we're just adding 238 plus 0, which is 238. On this side, we have 4 and 234. If I add 4 plus 234, I get 238. So the top masses here are the same, and the bottom atomic numbers are the same, which means that this is balanced and written correctly. All right? Number 85 says, explain in terms of elements why the nuclear decay of U234 to thorium-230 is considered a transmutation. So when you consider or you talk about a transmutation, you're transmutating, right? Or you're mutating. Think about mutation. Well, what does it mean if you're a mutant? Well, you're changing, okay? Specifically, you're changing the type of atom that you are. So a transmutation means that, well, if you have a transmutation reaction, that means that you're changing one isotope into another, okay? So an isotope of U turns into an isotope of thorium, or TH. Okay, an atom of uranium is changing to an atom of thorium, which is why it's called a transmutation, right? People throughout, pretty much the whole reason why people cared about chemistry is in the Middle Ages, they thought that they can transmutate things into gold and produce gold with them, right? And they were researching these transmutation machines. That's what they called them. And they were these machines or these chemical reactions that they thought would turn coal into gold, right? That's a transmutation reaction, changing an atom of one type of atom into another type of atom. So in this case, when uranium decays, it's changing from an atom of uranium into an atom of thorium, right? Which means that a different element is being formed. So you could have also said that a different element is being formed as your explanation. You could have also said that uranium has an atomic number of 92 and thorium has an atomic number of 90, meaning that you obviously changed the type of element. Or you could have said that an isotope of U becomes an isotope of TH. which is what I said. Anything just shows that you understand that a transmutation is whenever you're changing one atom into another. So that's the end of this video. Thank you guys for watching. If you have any questions, please feel free to let me know in the comments down below. If you like what you saw, please leave a like. Again, if you are studying for more regents other than chemistry, I do pretty much every single regents review out there. So check out the videos in the playlist or the playlists in the description of this video for more information. I hope you guys learned something, and I hope you have a nice day.